Hi, all. I'm going to be sure that I can get you a seminar by pre-recording this one. Hopefully, I'll also be live. We'll see. So, what we're doing today, what we're doing this week, Unit 4, the most interesting part to me at least, had to do with Big O notation. Now, Big O is becoming very practically important. A lot of the better employers now will ask you questions based on Big O. Things like that. Used to be considered to be very academic, but now it's considered to be very much part of a practical programmer's toolkit. And so we're going to have a discussion about Big O. I call this the Big O overview. So what it is, Big O is a way to measure algorithm complexity, typically in terms of time or space, but we're going to focus on time. Most people do, okay? Why we use it. It provides a quick way to assess whether an algorithm makes sense in a particular context. Typically, we're talking collections and we're worrying about how big the collection is, so it's often related to the size of a particular input. You can use it for more specific things, like if you have a complicated arithmetic expression, you could come up with a Big O for that, but that's not normally how it's used, and that's not how we're going to do it. Now, a quick way to assess, a lot of people don't like Big O because they say it's not, well, let me wait a slide or two. Big O can point out bottlenecks that encourage us to consider or choose different approaches. Years ago, there was a case where a company was using a sort, and what was happening is it was taking all night to run their sort. This was back in the 60s. And they hired a consultant. What the consultant realized is they had a large volume of things, but that the first thing they needed to sort them by had to do with which state the mail was coming in from. They would get mail in and they would open the mail and they would key it in, and then they would sort it, amongst other things, by zip codes. And there aren't any zip codes that extend across states. And so the sort was so slow because of the number of elements. So what he figured out was he went down to the local post office and he got them a PO box, one for each state that the company did business in. And then he had that go on to the reply envelopes that were sent to customers that were creating the problem. And so the mail from different states would show up in different PO boxes. And then what the program would do is it would do a sort within that by zip, but just for one PO box at a time. So he'd basically divided it up without using any computer time by state. So he had pushed a lot of the work of sorting the mail off onto the post office. He focused on this because he realized in analyzing the Big O that the thing that was taking most of the time was the sort, and that the sort was very sensitive to having more. And so if he could make the sort smaller, even if he had to do more sorts, he was going to come out ahead. This is the sort of thinking that Big O sets us up to do. Using Big O can help us avoid futility, avoid trying a problem that really can't be solved. One example is the class scheduling problem, okay? If you've ever done course schedules, and I'm thinking primarily of an on-campus kind of a deal, but it could happen to you online as well. You have this problem if you're taking several different courses that they'll be during the same time slot. And you might ask yourself, well, you know, they're only offering this course once and they're only offering that course once this semester. Why can't they put them into two different time slots? It turns out that the Big O of doing things like that is extremely large, and that it would take more computer time than anyone has available to do it. And so by understanding the Big O of approaching that problem, we don't have to spend a lot of time trying to write the program and seeing how well it works. We can say this is a non-starter. We don't even need to go there, okay? What Big O should not be. It's not a way to benchmark, okay? It gives us a big picture on how long a program will take to run, but it's not counting clock cycles, okay? And whether this is important to you depends on what you're doing. For instance, operating system people, they're very picky about individual clock cycles because they know their work is going to get used by millions of people, and rewriting something to save just a few computer clock cycles is going to be worth doing. But for most of us, for what we do, it's not. And also, it changes around too much. If we move to a different processor, it changes. If we get a new patch of the operating system, it might change. So the lack of detail in Big O is actually a feature and not a hindrance because it keeps us focused on what the big picture is. Big O is independent of hardware, and that's another feature. If someone gets an iPhone 10 instead of an iPhone 8, we don't want to rewrite all of our code. We want to say, well, you know, it's faster and that's great, but the bottleneck is still the bottleneck, and we measure that by the Big O. Also, we want it to be independent of the details of a particular problem. We want to see big picture thinking. And we want it to mostly be independent of data values. So, for example, with sorts, some sorts, if the data they're doing is almost in order to begin with, their performance changes a lot. And in some, if they're sorted or mostly sorted in the reverse order of what you want, if they're going descending and you want ascending or something like that, they have unusually bad performance. And in some cases, this is so dramatic that we have to take that into account, and we have to have sort of a checklist of using a particular sort and say, hey, is your data almost in order? Is your data almost in reverse order? If so, this sort is probably not a good choice for your purposes. But in general, unlike a benchmark where we might spend a lot of time saying, yeah, but if the values are more like this, it changes the runtime, we want to just say, you know, if we've got 1 million customers, it's going to look something like this. And we're not so worried about, are their names spread out nicely? Do their names, most of their names start with an A? We don't want to get into those details, those kinds of weeds. So in general, Big O looks at classes, that's groups of complexity such as constant versus linear versus squared. A rule on Big O, and I'll show you an example, is that once we figure it out, we ignore the constants, and those can make a difference. We'll talk about that in a minute. It really is a big picture kind of a thing. So we'll take just a few minutes, and we'll look at Big O for collections. And what we're talking about is we're looking at where n is the number of objects in collection, a particular collection, and mostly we want the average case. We don't want the worst case or the best case. Once again, some sorts, if it's already in order, it would run really quickly, but we don't want to consider that, okay? So let's try to look and see what we're talking about here. Okay, we're going to start with something fairly simple. This is a linear search, and the linear search, I'm just going to check something. Am I recording? I must be recording. Yeah. Okay, so we're going to start with a linear search. This is a little bit of linear search code. This should be fairly straightforward. This is not a particular language. You know, this is a general code. We call this pseudocode. So we set found to false, and then we start through our array to the number of size. So however many items we have in an array is our size. We go from 0 to the size. And if the particular element is what we're looking for, then we set found equals to true. And then when we get done with our loop, we return found. So we're going to look at each item one by one until we find what we are searching for. So if we have twice as many items, it's going to take twice as long, right? So if we have 1 million items and it takes so long, looking through 2 million items is going to take twice as long, okay? Now, we could return as soon as we found the target. Now, if we assume for a moment that the stuff we're looking through is random, the values are in a random order, in the average case, we're going to find what we're looking for halfway through. right? Now, sometimes the very first thing we look at is going to be the one we're looking for. It's going to be really fast, okay? It could be really fast. In other cases, it's going to be the last thing. But on the average case, it's going to be n minus 2. Now, this is not really the case with this code. Why? Because we keep going until we go all the way through. So this is always going to take twice as long, okay? It's going to take twice as long if I have twice as many elements, even if the thing I'm looking for is the very first element. We could improve this program quite a bit by changing this line where found equals true to a return line. You know, we could just return out of this right here or stop the loop somehow with a break statement. Either of those would work. But if we stop as soon as we find the thing, then sometimes we're going to get lucky and it's going to be much quicker. And on average, the average case, if we put a break in here, is going to be big O n divided by 2. Now, is n divided by 2 the big O? I would say no. Some people would say yes. I would say no. This is an example of one of those constants, okay? So you say, well, I'm cutting the time in half. Isn't that significant? Yes and no. You can cut in half, but if you double the number of items, it's still going to take twice as long. So the normal answer by theorists, not by operating system people, is that the constants don't change the big O. So even if we put the breakpoint in here, we're not going to start saying, oh yeah, linear search has a big O of n divided by 2. We're just going to say big O has linear search has a big O of n, okay? We're not going to worry about the divide by 2 because that's just a constant, okay? It's not based on n. So let's go on and see some other examples. Here's a binary search. This is another thing you're looking at this week. Now, running one of these, we have to start by assuming the collection is sorted. If it's not sorted, we need to sort it first or it won't work, okay? We're going to start in the middle and we're going to go higher or lower. So it's much like playing a guessing game. So suppose I tell you that I'm thinking of the number between 1 and 100 and I'm going to tell you if it's higher or lower. A good guess is something like 50, right? So let's say that the number that I'm looking for is 33, and I tell you it's a number between 1 and 100. So you guess 50, and I say lower, okay? Well, now you immediately know that it's not 51 to 100. We get to ignore half of our values. We throw away half of the numbers because of that guess. So I say it's lower. So now you know it's between 1 and 50. So let's say you guess 25, okay? But it's 33. So I say higher. Okay. Well, now you can throw away from 1 to 25. So with that guess, you're throwing away half of the remaining numbers. Okay. So higher. So now I'm going to try to pick a value that's halfway between 25 and 50. Okay. And so that's about what? That's about, let's say that's 32, okay? So I guess 32, and I say higher because it's 33. So you break between 32 and 50 in half again. You can see what I'm doing. I go through half each time, and after a little while, I will zero in on the number, okay? So in general, if we can break our collection into groups and then eliminate whole groups from consideration in one fell swoop, our efficiency goes way up. Okay, that's often an approach that's applied to algorithms. Let's see how powerful this is if we throw away half at a time. Comparisons needed in a binary search. Well, if I had 10 numbers, they were sorted, and let's say I'm doing a linear search, which doesn't take advantage of the sorting, but I can run a linear search, right? Depending on the number I'm looking for, on average, I'll look at 5 numbers. Now, binary search, I only need 4 numbers, but you know, that's one number comparison. If you've got a modern computer, you don't really care. But look at what happens if we have 100 numbers, like our example. In this case, the number of comparisons for a binary search will be 7, but if I was doing a linear search, even if I quit when I find it, even if things are randomly distributed, on average, I'm going to take 50 tries versus 7. This is getting better. Let's skip along a little bit. Let's look at this last number. This is 100 million. Now, 100 million, if I'm doing a linear search, well, if I'm doing one that's kind of badly written, it'll take 100 million comparisons. But even if I'm doing one that quits when I find it and they're randomly distributed, the things I'm looking for, on average, that'll be 50 million comparisons. And for a binary search, I'll need 27. So you can see this is a very powerful approach, a very powerful approach. Now, what kind of big O is this? Well, as I said on this slide here, but I didn't have a chance to explain it yet, this is a big O of what we call log n, and that's going to seem confusing. But the way a log works is basically if I throw away half of what I'm considering for each comparison, which is what we're doing here in binary search, it's going to end up with this pattern I showed you here, and where things go up very slowly. And that's if we work out the math, that's going to be log n. But rather than trying to work out that math, just intuitively look at something, and are you typically throwing away half of the numbers each time? Now, there are a few cases, half is by far the most common. There are a few cases where you're throwing away, you're breaking into 3 groups and you're able to throw away 2 of them, in which case you only have a third of the remaining groups. That's also a big O of log, but that's log to the third n. If we don't specify, we mean it's log to the second n. So, but for our purposes, if you know that throwing away half of the things consistently gives you a big O of log n, you're ahead of the game. You're where we need you. Okay. Here's a bubble sort. This is the most common sort taught. It's become kind of, jokes are made about this. They set Barack Obama, when he visited Google, they set him up with a question so he could show off, and everyone knew it was a setup, and they asked him about doing some sort, and he says, well, you don't want to use a bubble sort. So it's become presidential humor. So this is a bubble sort, and what I want you to notice is that we have a nested loop, right? I've got 2 for loops, and one for loop is inside the other for loop. Okay, if we look for a moment just at the inner for loop, the inner for loop goes the length of the array pretty much. And so that means that the inner loop by itself would have a big O of n. But if we only go through our array once swapping numbers, we're not done yet. We have to go through it more than once. Now, at the end of each pass, we will have finished getting the number on the extreme right. We'll get the biggest number all the way to the right. And so we don't have to look at it again. And that's why in this inner loop, it says list count -1. Every time we go through the loop, the number of elements we have to consider gets less by 1. So how many times do we do? So the thing is, we have to do the inner loop more than once. And how many times do we do it? Well, we do it n-1 times, okay? So where does that put us? So we do something that takes n times, and we do it n-1 times. We're throwing away the constants, okay? So that means that we do n times through the loop, and n times n is n squared. So this bubble sort has a big O of n squared, okay? This is not a good situation because as the number of n increases, the amount of time it'll take will go up very quickly. So this is the sort of thing that we would like to avoid. We would like to look at this and say, you know, this thing with the nested loops based on the number of things we're looking at, this is going to become a bottleneck. The length of time is going to go up very quickly. This one's n squared. If I had, for some reason, yet another nested loop, which we don't here, that would become n cubed. There are some algorithms that are n cubed. There aren't too many of them because they're very slow. Beyond that, we normally just don't do them in normal computing. We'll talk about some exceptions in a minute. So this is as bad as we want it to get. Now, there are some sorts. Most sorts require n squared. It's very easy to develop an n squared algorithm for a sort. There are dozens of them out there. Some of them are a little bit better, but they're still all n squared in big O, so we don't really worry about the difference. There's a quick sort, and I believe in this course you get to see a quick sort. I think we give you the code for it. And it does better than this. It does, it breaks the things you're sorting into groups and considers the groups separately. As we talked about, when we break things into groups, do a lot of small sorts instead of a big sort, we gain some efficiency. And so a quick sort ends up with a big O of n times log to the n, which I don't think you need to know for this course, but and that's as good as it gets. It's been shown mathematically that you cannot do better than that, okay? But this is much more common. Now, if we use a sort from a language library, they're almost always quick sorts. And if they're quick sorts, then they're going to have this n to the log n, n log n performance instead of n squared performance. That's going to be much better than we're likely to come up with by ourselves. So you want to do that. And that's an example of looking through something and finding a bottleneck and saying, hey, look what we're doing here. We've got a loop inside another loop. That's not good. Okay, so here's the big picture for what I'll call conventional programming. And what we're looking at is the number of items versus the number of steps, the amount of time it takes. Number of steps would be the amount of time it takes versus the number of items. And let's start by looking at this spot marked A. That has a big O of n squared. And you can see that goes up very quickly. As I increase the number of items, the amount of time it takes goes up very, very quickly. And the bubble sort's an example of that. Then we have line B. Line B is a straight line. It's a linear line. I happen to draw it at a 45-degree angle. That's not necessarily the case. That's typically the case. And I'll tell you about that in a second. But basically, as I add elements, it gets bigger. It gets bigger in a linear way. So if it takes an hour to sort 1,000,000 items, it'll take 2 hours. Or I shouldn't say to search 1,000,000 items. It'll take 2 hours to do 2,000,000 if it's a big O of n. Now, if I want to factor those constants in, which I said we don't normally do, then I could get a different slope on this. For example, if I do that modified linear search where we quit on average halfway through it, and I divide this n by 2, I would get a different slope to this line. But if I double the number of items, I'm still doubling the number of time. Okay. Line C shows you what happens when we get a log n when we're throwing groups away. And you can see it goes up, but it grows up very slowly. You remember my example where 100 million elements only took 27 comparisons. And finally, we have some things. We say they're a big O of constant. We write it as big O of just 1. That's something that's independent of the number of items. For example, in C# and Java, when we have an array, we have a variable that keeps track of how big the array is, how many things are in it. If I'm keeping that in a variable and I say, how big is my array? It just returns that variable. It returns that variable whether there's 1 item in there or 10 items in there or 1,000,000 items in there. It takes the same amount of time. So that's a constant big O. So if you have this graph in mind, if you understand this graph, you know what you need to know about big O in general for the real world. There are a few algorithms. They mostly involve graphs, which we don't cover in this course. I'll give you an example in a minute, that have a big O of n to the third. We won't talk much more about those. I'll give you some other examples of where things can get bigger. So we have problems that are called hard problems, and that's not just they're hard for you. That's a mathematical term. And we have people that are complexity theorists that study these problems. And they come up with some interesting things. They're beyond this course, but I just thought I would give you something to think about in your spare time. You won't need it for this course. One is the traveling salesman problem. This seems very reasonable. It's named after the idea. Let's say we have a salesman and he has a bunch of customers and he needs to visit each one of his customers and then he needs to come back home. And he would like to do this in the shortest distance or maybe the shortest amount of time Or maybe if he's buying plane tickets, he wants to do it at the least cost of the plane tickets. Doesn't matter. He wants to minimize something, right? And he wants that in the minimal amount of time. Well, it turns out that there's not a nice, neat way to do that that will guarantee you that you'll come up with the optimal result. In general, to come up with the optimal result, we have to take, for each city we add, we have to check all the possibilities of which order it should go in, and that gives us a big N to a factorial. So if the cities we're visiting were 7, we'd have 7 times 6 times 5 times 4 times 3 times 1. Because each time we put a city into place, then we don't have to consider it again. But you can see that number gets big even more quickly than n squared. There's a special case for Euclidean space. I won't get into it, but you see it's still a mess. It's still very large. Now, there's a heuristic case. Heuristic means a rule of thumb. There's a rule of thumb case where it's called plane cutting. I won't go into it, but this allows you to cut the number of comparisons you have to make. And it doesn't give you an optimal result, but it'll give you within 5% of optimal, and it runs in n log n time. So for instance, this is a very practical problem. For instance, a company like UPS or FedEx, they're paying people to deliver packages. They would like to give them the order to deliver packages in such that they drive the least amount, right? That seems very practical. They don't have time to run this big O that's a factorial. They would take longer calculating it than they have to deliver it, because they basically have to come up with a new list every day. But this plane cutting, which is reasonably fast, that's within 5% of the best route. Occasionally they'll get an order that doesn't give them optimal, but on the whole it's good enough for them. Here's another one that's sort of famous. It's called the knapsack problem. Given a number of items and each has a weight and a value, and we're trying to put them in a backpack so that we don't overload the backpack. The backpack has a maximum that it can hold, and we want to take the most valuable things and still fit them into the backpack. This may seem like a party game, backpack, how hard is it? But for instance, if you're trying to load a container ship with containers, this could be very important. And you might have 100,000 containers on a container ship. You need an efficient solution. Once again, if we do it straightforward, we just say, well, let me try some and see how it works, and let me try something else, you'll end up with this big O of n factorial, and that will just take too long. And there's something called dynamic programming, which we won't get into this course, where they can get it better. They get it to n times w, where n is the number of objects and w is the size of the knapsack. The weights have to be positive. Those are pretty reasonable. So that's a shortcut. It won't work for all the problems. You can use it. Another example of a problem you can do with this is, let's say you're running a printing company, right? And so you have a printing press, and it can print so many things per day, right? And you want to take print jobs that maximize your profit. So if someone calls up and says, I'd like you to print this, and I'm willing to pay this much, should you take that job or not? Well, you got to fit them in. It's the same problem, really, as fitting these weights into a knapsack. And so this is a very practical kind of a problem. We'll look at just one or two more. This one's called the Knight's Tour. Knight's Tour, it's a sequence of moves by a knight on a chessboard such that the knight visits every square only once, and visits all the squares, so exactly once. The big O on this is k to the n, where n is the number of squares on the board. So this would be, so this gets big in a hurry, okay? You got some constant, and then you raise it to the power of number of squares on the board. So for example, on an 8 by 8 board, 8 times 8 is 64. So you have some constant to the 64th power. You get this big number, right? Assuming a computer makes 1 million moves per second, it would take 1 million years to solve this problem in a brute force way. And people have come up with some shortcuts on this. But, it's interesting that you can take what seems like a simple problem and make it big. Okay. In fact, let me mention this about chessboard problems. There's a old story originated in India, and of course it's a story. It didn't really happen. But in the story, a peasant does something great for the emperor, and the emperor offers to reward him with anything he wants in his kingdom. But of course, the peasant is savvy enough to realize that he doesn't need to appear greedy. That'll just get him into trouble. So he wants something that'll seem like a very modest request, but will actually give the peasant a lot. And so what he says is he sees a chessboard and he says, "Oh, I'd like you to put a grain of rice on the first square in the chessboard, and I'd like you to put 2 grains of rice in the second square and 4 in the third. And so for each square, I want you to double the amount of rice that was on the previous square." Well, this seems, he's the emperor. This seems very reasonable. It turns out, though, if you do that doubling 64 times, that you're asking for more rice than exists in the whole world. When you double things, the numbers go up very quickly. And it's good for us to note that and be aware of that when we come up with proposed solutions for things, because if we have numbers that are all big, even 64 is not a huge number. If we've got one of these situations, we're going to end up with a solution that's not very practical. Okay. Last problem. This is the 8 queens problem. It's another chess problem. It's amazing that chess, which seems pretty straightforward, has come up with so many problems that turn out to be very hard. So the idea is you want to place 8 queens on a chessboard so that no 2 queens threaten each other. Now in chess, a queen can move and attack a piece anywhere on the same row, anywhere on the same column, or anywhere on either diagonal. So a queen can move in 8 different directions, okay? And we want to set up so that no 2 queens will actually run into each other. And this shows an example where we have it where no 2 queens can get each other. So we could just put queens and then try a different position, try a different position, try a different position. If we're looking to find all the solution to the 8 queens problem, there are, let's see, what is that? Hundreds, thousands, millions, billions. There are over 4,426,000,000 possible arrangements of 8 queens on an 8 by 8 board, but there are only 92 of them that don't attack each other. So knowledge about the problem, we can reduce the number of moves. We use a heuristic. For instance, there's no point in putting 2 queens in the same row. That will never work. If we're putting queens out and we get to a point where we put 2 of them in the same row, we just give up right there and try again. Same with the column. And so we can greatly reduce this, but it's quite a hard problem, and it doesn't seem on the surface like it should be. Now notice this problem has a big advantage that while it's hard to find a solution, it's fairly easy to check and see if the solution that you think is right actually is right. And that turns out to be a big advantage. Okay, finally, I'm going to close with this. There's this really excellent video about this problem. It's called the P versus NP problem, and I'll let the video explain what that is. But that's the ultimate complexity problem, and actually there's $1 million award if you can prove it one way or the other. But it's called P versus NP in the Computational Complexity Zoo. That's the URL for it on YouTube. I think it's about 10 or 15 minutes long. It's not horribly long. It's really well done. And one of the very interesting things is it has a good explanation as to why solving these big O problems can be important, besides the fact that we're just all impatient and want things to run faster. So I hope this has been a good intro to big O for you. It's kind of cleared it up. Without a good explanation, it can be a little muddy. We'll see ya.